let's move on and look a little bit at some of the different types of forces we can encounter in dynamics problems in our course. And so this is one place that students can get stuck, is knowing exactly what kind of forces are acting. And so just a couple of definitions. So tension is a pull from a rope. Gravity is the pull between two objects. We'll talk more about that later. And then there's contact forces between surfaces. And these get broken into two different kinds, the normal force and friction. And so let's go through and do a couple of examples with these different types of forces. So surface contact forces come up a lot. So when an object comes into contact with a surface, like the block on a table below, there'll be two forces, the normal force and the frictional force. And those are defined this way here. So normal force is the one that's pressing up between the table and the block, and the frictional force will be going in the, if we break this into sort of a y and an x direction, and in the x direction, or parallel to the surface. And of course, it depends on which way or whatever is happening to the object. We will spend a lot of time talking about friction, but that's how we break it down. And for instance, what'll be real common, and we've already started looking at this, would be say an inclined surface. And so what happens here, right? If we incline this, it's the same sort of rules. There's a force that's normal. Again, that's like it's pushing, perpendicular or normal to the surface, and the frictional force, which is going to be the force that's going to be parallel to the surface. And so whenever two objects come into contact, there's the possibility of these two forces being applied. So normal force is always perpendicular to the surfaces, and the frictional force is always parallel to the surfaces. And of course, this can get tricky when you start, changing the surface like we do here by inclining it or something like that. The force of gravity, so this was a force that was sort of figured out by Newton, and it's the force between two objects. And so the actual force looks like this here. So the magnitude of the force is equal to g, which is a constant, times the mass m1, the mass m2, which are the masses of the two objects, and then r squared, where r is the distance between objects. When you go to the next course, 2b, you'll find that the force between charged objects has a very similar form. They look something kind of like this here, where the things that change is it's a different constant. So it's a k constant instead of this g constant, it's a different numerical constant. And instead of the masses, we're going to look at what we call q, which is the charge of the two particles. But besides that, there's a lot of similarities between these two forces. And g is this gravitational constant, which is this number right here. Now, we'll deal an awful lot with forces near the Earth's surface. Okay, and so here's kind of a little picture of that. And so this, you can imagine this is like the curvature of the Earth, and this is the object we're looking at, some mass m, and we're going to say this is Fg, some height h over here, where this r is the radius of the Earth. So what happens is, the radius of the Earth is in general much, much bigger than whatever height we can move this particle to. And so what happens is that even though, the force of gravity depends on the distance between the two objects, any sort of, or most of the time, little movements like 100 meters, 200 meters, whatever, whenever you can sort of say this here, that the radius of the Earth is much, much bigger than h, we can approximate the force of gravity to be that last equation we just did right here. And so again, this is our g constant. This would be the mass of the Earth. This is the mass of the particle. And then this is the radius of the Earth squared. Now what we can do is then, take this and we call it mg, where g is sort of our name for these constants right here. And so sometimes, this, if you go high enough, this can be not the best approximation, but for most things that we're going to do, this is going to be a really, really good approximation because, again, the radius of the Earth is so huge. And so, again, this g, we've already started using it, is this big G, the mass of the Earth divided by the radius of the Earth squared, which, of course, we know is 9.81 meters per second squared. And so this will be our force, the gravitational force near the Earth's surface. So the force on the object from the Earth is equal to mg. So sometimes we'll sort of break these forces up into a manner like that, where the force sort of specifies the object that's applying the force and the one that's feeling the force. And so just a real quick example gravity problem. Here's a student sitting at a desk. She will have a force due to gravity of Fg. And so a typical student mass might be, say, 55 kilograms. G, of course, is 9.8. Now, yeah, so this is, sometimes we use 9.8, sometimes we use 9.81. It doesn't really make too big of a difference. I don't think there'll be many problems where it will for us. So use whatever one is easier for you. And so when we do this, Fg is equal to m times g, 55 times 9.8, and we get 539 newtons. And the force that gravity exerts on any object is called its weight. And so this person here has a weight of 539 newtons. Now, of course, these are the SI units, which are almost always what we're going to use. The units that we use for ourselves are pounds. Pounds is a unit of weight in our system. But again, we won't really deal with that much. But just so you know that that's sort of the equivalent of Newton would be a pound. And so let's just do some quick examples. So Newton's second law. So here we have a box of mass 3 kilograms lies on a frictionless surface and is pushed by a constant force of 25 newtons. What is the acceleration of the box? If the box starts at rest, how long before it travels 3 meters? So the way we approach these types of problems is the first step will almost always be, to draw a picture and figure out what forces are acting on the block. And so here we've got the force of the 25 newtons. And so this next step is where we sort of draw what's called a free body diagram, essentially a picture that shows the different forces acting. And so on this thing here, there'd be the 25 newtons. Now, again, what we generally do, sort of break this into like y and x coordinates. Now, there would be a normal force pressing down and an mg, a gravitational force, the weight pulling down. Now, what's going to happen is in the y direction, these two forces would cancel in this case, and so they're not really a big part of the problem. And so what we want to focus on then is the x direction. And in this case, this is a pretty simple one. The force acting is 25 newtons. We're told that the mass is 3 kilograms, and so we can go through really quickly and find out that the acceleration is 8.33 meters per second squared. And then so the second part of this then is if the box starts at rest, how long before it travels 3 meters? And so in this case, we just use one of our kinematic constant acceleration equations. And so in this case here, we can say to ourselves, well, let's say I'll call my initial position 0. It says it starts at rest, so the initial velocity is 0, so both these terms go away. We know the acceleration is 8.33, and so we plug in 3 meters, and when I did this, I got a time of 0.85 seconds. So having just one force in the x direction is about as simple as it gets for these. And so let's make it a little bit more complicated. And again, this would be the x and the y axes. And so let's add another force of 15 newtons. Well, hopefully you can see that this doesn't change things too much. It would just be the difference between those two forces, 25 and 15. It's not to be 10. And so if we find the acceleration, it would be reduced acceleration of 3.33 meters per second squared. And so this, again, is the typical method that we're going to do. So the first step we'll usually do is figure out what the forces are. The second step, draw your picture. And then from there, you can generally go in and use Newton's second law to determine what it is you're trying to find. And of course, we'll do lots of examples moving forward from this. And so in this case, the forces work against each other and cause, again, the acceleration to be a little bit less. And so now let's stop and look at one that's a slight bit more complicated. So now there's 3 forces here. Again, this is a frictionless surface. Again, there is a normal force in the mg pulling down, but they just cancel out, so they're not super important. So what would the acceleration of the box be now? So go ahead and work this out, and then we'll talk about it. All right, so hopefully you got this answer here. And so when I figure this out, so this is again a case where you're going to want to use vectors. So we need to use our vectors here. And so if I do this, we look at the forces. So again, it's the same 25 and 15 before. And now here, the 30 newtons, right? I can think of it as being, there's a part of it that presses down and a part of it that pushes that way in the same direction as the 15. And the part that pushes with the 15, hopefully you can see, will be the cosine of that 30 degrees. And so when I add up the total of my forces, I get 25 minus 15 minus 30 cosine of 30, which gives me negative 16. So in this particular case, the forces pushing in the negative direction, right, are bigger than the forces in the positive direction. Again, this is my sort of standard XY axes. And so in this case, I'd go through and solve for the acceleration and get that it would be negative 5.33 meters per second squared. And so this is the gist of what we're going to do solving Newton's Laws dynamics questions. And so we'll do lots of examples in class. But just to recap, you add up the forces and the result equals mass times acceleration. And you can kind of think about this as like a battle of the forces. Basically which side of the forces will be bigger. And if there is an unbalanced force, there'll be an acceleration in that direction.